One thing to do, then to check out a meme. Wave particle duality. So what we're going to be looking at here is wave particle duality and de Broglie. So de Broglie had this idea. Scientist de Broglie had an idea. At this point in time in history, we have pretty convincingly proved that light can act as a wave. We've got single slit and double slit interference. We've got thin film interference. It's a wave. We've also pretty conclusively proved that light's a particle. Like, the photoelectric effect pretty much proves that right out. So, if light is a wave and a particle, then why can't all things be waves and particles? Like, you could make the argument pretty easily that this bowling ball is made up of particles, but can't this bowling ball also be waves? If light can be both, why not everything? This is like a fun Mikey theoretical. Just so happens that this idea works really well. We know that for light, the momentum of light is equal to Planck's constant divided by the wavelength. But we also know that for like actual physical objects, like a baseball or a bowling ball or you, your momentum is equal to a mass multiplied by some velocity. Well, if we just kind of work this around real quick, we can see that a wavelength equals Planck's constant over momentum, and that would in a way mean that it's Planck's constant divided by a mass times a velocity. And we're going to assume here that the velocity is much, much less. It's not even close to the speed of light, so that we don't have any relativity. But this de Broglie equation here, and this de Broglie wavelength that we've just discovered, has a kind of strange implication. Because light was a wave and a particle, and as a wave, we saw it interfere. Well, I know you're a particle, but if de Broglie is now saying that you're also a wave, then shouldn't you interfere when you go through like a single slit? Shouldn't you have interference when you go through a double slit? And that's even more messed up because how do you go through a double slit? Because you're one thing. This is actually a truly strange idea within the world of particle physics and quantum mechanics, but we actually see single electrons, when beamed at a double slit, will actually interfere with one another. And if you don't believe me, go check out a video on YouTube that shows this. I'll try to put a link in the bottom here. But we see these effects. We don't see it for you and I walking through doors a good single slit, because our velocity and our mass is such that the wavelength that we would be is super, super small. Planck's constant is times 10 to the negative 34. So this wavelength is very, very small, which means that in order to see a diffraction pattern or some interference, we need to go through a slit that is that small as well. And if we just make up some like bland numbers here, let's just pretend Planck's constant is 1 times 10 to the negative 34. It's really 6.626. And let's just pretend your mass is like, I don't know, 100 kilos, and you're walking at 1 meters per second. This would imply here that the wavelength that you would be at, or the width of something that you'd have to pass through, would be like 1 times 10 to the negative 36 meters. Which I can't exactly pass through that. I need to really step up my diet. Like, to the extreme. But an electron could. And we can, electron's going to have a different mass there, because the electron mass starts getting very small, right? It's times 10 to the negative 31st. So now we start seeing that this is just a very small number. It's like 3, 4, 5. And we start to see these effects. So this idea between the macro world not diffracting on a day-to-day basis, but the micro world for electrons actually doing these type of things is really wild. And it is a region of study that we're looking into in our current day and age. There are a few experiments. One is being led, or the initial idea was being led by Sir Roderick Penrose, where they were trying to take dust particles right on the border of being too big to diffract and being too small to actually do it. And they were trying to beam light at them and try to see some of these diffraction methods. He wanted to do his experiment in space. That's a little bit complicated. So there's actually some other individuals and groups that are trying to do this experiment here on Earth. But right now it's the year 2021, and they tried to get funding for this, I think in around like 2013, 2014, maybe 2015. They got the funding, but science moves excruciatingly slow. But we tend to be right whenever we finish. So last I checked, that group was still working on this project, still setting things up. But it is a kind of unknown thing right now. We know this de Broglie wavelength exists. We know it is a phenomenon that happens, that we actually see particles act as waves. But where does it take over that were particles, and when does it take over that were waves? That is a question for you. Until next time, though, we are finished here. Adios, and take it easy.